Hello and welcome. In today's lecture we will continue with the PI control of the heated surge tank, PI temperature control, and we will look at the case where the controller gain has been chosen such that the characteristic equation has two real repeated roots or two real distinct roots. We have already looked at the case of the characteristic equation having two complex conjugate roots. So here's our system to repeat. These are our base case conditions, and we are trying to control the temperature by using a PI controller that manipulates the heating duty to the tank. The process dynamic model is as shown there. This is the PI controller equation, and for the base case conditions shown here, the time constant tau is 10 minutes and the gain of temperature with respect to Q, or Q in percentage form, where the percentage has been taken with respect to the base case duty of 81.6 megajoules per minute, is 0.4. So now let's look at the case where you have real repeated roots. So let's start our process. Our governing differential equation, which we derived last time, we are looking at the case where the integral time for the controller has been chosen to be tau by r, where r is greater than 1, which basically means that tau I is less than tau. And the governing equation is second derivative of temperature, and T here is the deviation from steady state value and not the absolute temperature. And this gives rise to the regulator response, and this is the forcing function corresponding to the servo response. And we saw last time that the characteristic equation is lambda square plus lambda square plus 1 by tau times kkc lambda plus r kkc by tau square is equal to 0, and this has as its roots lambda is equal to minus 1 plus kkc divided by 2 tau plus minus square root minus 4r kkc divided by 2 tau. And we also saw that if kkc does not belong to this interval, and the interval is 2r minus 1 minus 2 times square root r times r minus 1, this is the lower bound, and the upper bound is 2r minus 1 plus 2 times square root r times r minus 1. So if kkc does not belong to this interval, then you have real roots and if I call this kkc min and I call this kkc max, then for kkc is equal to kkc min or kkc max, that means for kkc is equal to 2r minus 1 plus minus for these specific values of kkc, you get real distinct roots where this determinant goes to 0. So in this specific case, for this specific value of kkc, you get 2 repeated roots. And those 2 repeated roots are essentially lambda is equal to minus 1 plus kkc by 2 tau, and you also have the discriminant going to 0, so you will have 1 plus kkc must be is equal to 4r kkc. Well, we'll remove the 4. 2, you'll also have kkc. Okay, all right. So if you have these repeated roots, repeated twice this root, then if the differential equation written here was being forced by a step, then the solution of that differential equation forced by a unit step would be, so if you had a unit step forcing function, that means the forcing function is a unit step occurring at time t equal to 0, then my solution would be t is equal to 1 plus c1, and let me call this minus a, e to the power minus at plus c2 times t times e to the power minus at. This comes from the theory of ordinary differential equations. Just take it on good faith. We may also derive it at some point in time, but for now just take it on good faith. So this is the total solution for unit step forcing, and to get the c1 and c2 constants, apply initial conditions. So the initial conditions are t equal to 0 at time t equal to 0, and dt by the rate of change of temperature is 0 at time t equal to 0. So this implies temperature equal to 0 at time t equal to 0 implies C1 plus C2 must be equal to minus 1, and the derivative implies what does the derivative imply? Derivative implies minus a times C1, and the derivative there at time t equal to 0 will be plus C2. This must be equal to 0. So what this gives is that by the way, this term will not be there because we are multiplying by t. So what this gives is C1 equal to minus 1, and C2 turns out to be actually minus a, which is actually minus 1 plus kkc by 2 tau. So what we have is our solution for a unit step forcing is 1 minus e to the power minus 8 at. I will not use a, I'll use the entire thing there. So e to the power minus 1 plus kkc divided by 2 times t by tau, and the other term is going to be minus 1 plus kkc divided by 2. Let me just clean it up a bit. Divided by 2 times t by tau, and I'll erase this so that I have some space. Times exponential minus 1 plus kkc divided by 2 times t by tau. So this is my unit step response. Now if I want the regulator response, then you can see the regulator is, and if I call this equation A, then the regulator response will be tau by r kkc times derivative of the unit step response. So I'll get t will be equal to tau by r kkc times derivative of the right hand side of the above equation. So if I differentiate a, what I get then is, I'll have to take the derivative of this, it will be t will be equal to tau by r kkc times the derivative will be 1 plus kkc divided by 2 tau times e to the power whatever. We'll put that in later, and the derivative here would be okay, so 1 plus kkc. So derivative with respect to time, if you differentiate the first term, you'll get minus 1 plus kkc divided by 2 tau, and if you differentiate the exponential, what you'll get is plus 1 plus kkc divided by 2 tau whole square times t, this whole thing multiplied by e to the power minus 1 plus kkc divided by 2 times t by tau. So this is the regulator response, and you'll see that this and this cancel out, and because of this cancelling we get a very, we will also invoke this, equation right here, and if we invoke this, then 1 plus kkc whole square is actually 4r kkc. Yeah, so what we get is T regulator is equal to tau by r kkc, and 1 plus kkc whole square is actually 4 r kkc divided by 4 tau square times t e to the power minus 1 plus kkc divided by 2 times t by tau, and this cancels out, and this cancels out. So what you get is T regulator, very neat response, is equal to this, and this cancels out, is equal to T by tau and you can also substitute this guy, you can also substitute this guy over here, and then what you will get is T by tau times exponential of 2 and 2 will cancel out, then r plus minus square root r into r minus 1 t by tau, and you got a negative sign here. So this is the regulator response for PI control of the heated surge tank, PI temperature control of the heated surge tank. Regulator response for PI temperature control of the heated surge tank using a tau I that is less than tau and kkc chosen such that you get real repeated root. If you want to get the, what shall we call it, if you want to get the servo response, we proceed in a similar manner, and maybe we'll do it right now. So if you want to get the servo response, then I'll just erase the regulator response part. So if you want to get this so now to get the servo response, what we will have to do is tau I times derivative of the unit step response plus the unit step response. That's what we have to do. So for the servo response, if you want the servo response, for the servo response, we will have T is equal to A RHS plus tau I, and tau I is actually, if you look at this guy, tau I is tau by R, yeah, so plus tau by R times derivative of time derivative of the right hand side of equation A. We already derived the time derivative, and the time derivative, so what we had there was, let's just do it, tau by R okay, so let's just do it. So T will be equal to tau by R times time derivative of the right hand side of the previous equation, which is yeah, other terms cancel out. The only term that remains is, yeah, the with the T, yeah, so it will be 1 plus KKC divided by 2 times tau whole square times T and you'll have the exponential, so we'll just call it e to the power minus 80 for the time being. Yeah, so this term is there, and then so this is the this is from the derivative, and then we have the plus 1 minus e to the power minus 80 minus oh minus 1 plus kkc by 2 is a, so minus a यार ये a के चक्कर में गड़बड़ हो जाएगी, छोड़ो, a सिर्फ एक्सपोनेंशियल में रखते हैं, so we'll just keep the a in the exponential, minus 1 plus kkc divided by 2 times t by tau into e to the power minus 80. Okay, and so if you do some algebra, we'll get t is equal to 1 minus so there are so I'll take e to the power minus 80 common because that's common to all the terms. So then I'll get 1 over here, that's corresponding to this guy, so this guy is done, and what, this guy is done, and then what you do is take 1 plus kkc by 2 common and t by tau also common. So let's just say I will take, because this is minus, so I'll take minus. So minus 1 plus kkc divided by 2 times t by tau. So that takes care of this term. And what will be left here will be, so if you take this term common, then that would be 1. And then we are left with this term, and this term, because it has a positive sign, would be minus. भैया ये क्या किए हो यार? I think I've blundered. Well, acha, 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 acha. Okay, okay, okay. Because this is minus. Okay, so that's why the sign was getting. So, okay. So this term would be so this would be minus 1. So minus into minus into minus is negative, so that takes care of this. And the next term is, after all the multiplications, it must be positive. So minus into minus is already positive, so we will have plus. And we've taken 1 plus kkc by 2 tau common, so we will be left with 1 plus kkc by 1 plus divided by 2, and there is a multiplier by tau by r, so r will be left, and t by tau has already been taken out. So this is what we are left with as far as I can tell. And so what you get is t is equal to 1 minus 1 plus kkc by 2 times t by tau into 1 plus kkc by 2r minus 1. And maybe we should keep the functional terms in the end as a convention. So we'll have t by tau over here, and e to the power minus 1 plus kkc by 2 times t by tau. So that's the servo response. And if I substitute the value of kkc over here and do some of the necessary algebra, then what we will get is t is equal to 1 minus, you see, 1 plus kkc is going to be, and 2 will, so it is going to be r plus minus square root r times r minus 1, the 2 will cancel out. And then if you take a look at this guy, so 1 plus kkc by 2 is going to be this guy, and you divide by r, so that will be 1. So 1 minus 1, that will cancel out, so you are left with this term, divide by r, so it will be square root r minus 1 by r. Okay, so the next term is square root r divided by r minus 1, but you got to have a plus minus there. So let me just do a little bit of, so you have this guy plus minus square root, yeah, t by tau and then you get exponential of minus r plus minus square root r times r minus 1 times t by tau. So this is the servo response. Servo response. Just to summarize what we have done, let's take a look at, so as I told, as we did, for kkc is equal to these specific values, you get two repeated roots. The governing differential equation is this. Regulator, servo, characteristic equation roots are here. The discriminant is 0 when kkc takes these special values. So for these special values, you get these two repeated roots. For these repeated roots, the homogeneous part of the solution is c1 e to the power lambda t plus c2 times t e to the power lambda t, and for a unit step forcing function, the particular solution is 1, and therefore your total solution is particular solution plus the homogeneous solution. So that's this, and the initial conditions give c1 equal to minus 1 and c2 equal to lambda, yeah, c2 equal to lambda, yeah, with the negative sign. Okay, yeah, fine. And well, and that's that. So the unit step forcing response turns out to be this, as we derived, and after doing the necessary algebra, tau by r kkc times the differential of the right hand side here gives you the regulator response as follows, and tau by r times differential of the right hand side here plus the right hand side gives you the servo response as this. So these are our regulator and servo responses for the heated tank temperature control using a PI controller problem. Now it'll be very rare that you get exactly same roots, distinct equal roots. More common would be, either complex conjugate roots, which we have handled, or real distinct roots. So now let's look at the case where you have distinct real roots. Distinct, this is the case that we are now looking at. And what are the roots? The roots are lambda is equal to minus 1 plus kkc by 2 tau plus minus square root 1 plus kkc whole square minus 4r kkc divided by. So these are the two roots, and if the discriminant is greater than 0, you get two real roots, and these two real roots may look something like this on the complex plane. you know, the first root is this guy and the second root is maybe this guy. Yeah, so if you take the plus part, then you'll get minus a, and if you take the minus part, then you'll get minus b. So these are your two distinct roots, and let us call them lambda is equal to minus a and minus b. Magnitude of b is greater than a. Okay, now if you have step forcing, for step forcing, what you will then get is t is equal to 1 plus c1 e to the power minus at plus c2 times e to the power minus bt, and the initial conditions imply c1 plus c2 should be equal to minus 1. At time t equal to 0, the temperature is 0, or the deviation in temperature is 0, and at time t equal to 0, the rate of change of temperature is 0. So rate of change is at, it will be minus a times c1 minus b times c2. This should be equal to 0, and what this does, it gives c1 is equal to minus b divided by b minus a, and c2 is equal to minus a divided by a minus b. And so our unit step temperature response is T is equal to unit step temperature response is 1 minus b over b minus a e to the power minus at plus a over b minus a e to the power minus bt. So this is the unit step forcing response, unit step. So if the differential equation was forced by a unit step, this is the response that we would get. The regulator response is going to be regulator response, we will call this equation A. The regulator response is going to be tau by r kkc times the derivative, time derivative of the right hand side of equation A. Now if we do that derivative, so we will get t is equal to tau by r times kkc times ab times b minus a times e to the power minus at, and there you will get minus ab by b minus a e to the power minus bt, and that gives you t is equal to tau by r kkc times ab divided by b minus a e to the into e to the power minus at minus e to the power minus bt. And then if you look at a times b, if you look at a times b, that's, you know, plus minus the first and the second, multiply the two, that will be a square, you know, this guy square minus this guy square, and when you take the squares, the 1 plus kkc term will cancel and you'll be left with 4r kkc, and this becomes 4. So this would actually be so a times b is going to be r kkc by tau square. and b minus a, this guy will cancel out and you'll be left, and so b minus a is going to be square root 1 plus kc whole square minus 4r kkc divided by tau. So you substitute these things into this guy, so hopefully what you'll get eventually is that T regulator is equal to, when you substitute it, do you see the taus will cancel out, the r kkc will cancel out, yeah, and you'll be left with 1 over square root 1 plus kkc whole square minus 4r kc into e to the power minus at minus e to the power minus bt. Now see, if you look at the roots, you have e to the power minus at and you have e to the power minus bt. E to the power minus at, see, magnitude of a is smaller than the magnitude of b. So if you look at e to the power minus at at time t equal to 0, magnitude of both e to the power minus at and e to the power minus bt is going to be 1. So 1 minus 1 will be 0. So at time t equal to 0, you got a 0. And then if you see, e to the power minus at will decay, will decay, e to the power minus at will decay slowly because a is small magnitude, whereas e to the power minus bt will decay faster. So when you, so this would be e to the power minus at and this would be e to the power minus bt, and when you add the two up, pointer ink color, when you add the two up at time t equal to 0, so eventually everything will disappear, and so what you will get is a response that looks something like this, eventually things disappearing. So this is what the regulator response would look like. Yeah. Okay, so that's that. Now let's look at the servo response. If we look at the servo response, so maybe I'll just erase this, oh sorry, I will just erase this part. The servo response will be obtained as tau by r times derivative of the right hand side of equation A plus the right hand side of equation A, and if we do that and do the necessary algebra, hopefully what we will get so the right hand side of equation A is, so servo response, I'm sorry the color has changed, so the servo response is going to be t times, t will be equal to right hand side of equation A, which is 1 minus b over b minus a e to the power minus at plus a over b minus a into e to the power minus bt plus tau by r plus tau by r derivative of the right hand side. So derivative of the right hand side is going to be, what's the derivative going to be? Yeah, we derive the derivative as ab times b minus a times e to the power minus at minus e to the power minus bt. And if you just take the common terms, what you should get is t should be equal to 1 plus b over b minus a into a tau by r minus 1 into e to the power minus at minus a over b minus a times b tau by r minus 1 into e to the power minus bt. So that's your servo response, and you can see that as time goes to infinity, the exponential terms go to 0, and so if you have a unit change in the set point, then final value is going to be 1. So if you give a unit change, your temperature is going to eventually end up at set point. Alright, so much for the derivation. So I'll just quickly summarize. So we are looking at the servo response and the regulator response. When the characteristic equation has distinct roots, it will have distinct roots when the discriminant is greater than 0, and the first root we'll call minus a, the second root we'll call minus b. Magnitude of b is greater than a, so the solution is going to be of this form. The coefficients are calculated using initial conditions, and so you get the unit step response. Regulator response is obtained as tau by r kkc times derivative of the unit step response, which gives us this, and the servo response is obtained as tau by r times derivative of the unit step response plus the unit step response itself, which gives us this. This is what we have derived. Now let's look at, as you change the tuning, what kind of responses you get. So if you have a P controller with kkc is equal to 3, the response is this blue curve. If you have a P controller with tau I is equal to tau and kkc is equal to 3, you get the magenta curve. That's this, reasonably smooth. If you have a PI controller with R equal to 2, that means tau I is tau by 2, you see you start getting oscillations, you start getting an undershoot. And as kkc is increased, you again see that the aggressiveness of your control action increases as kkc is increased. So the common feature is there is no offset with PI control, whereas proportional control gives you offset. Overshoot is possible with integral action. And if you look at the responses, the servo response seems to be completing faster than the regulator response, and that is because the regulator response, it takes time for the error to develop in the process variable before the controller starts really acting, whereas in a servo response, as soon as you change the set point, there is error in the controller, and therefore the controller starts acting. And so you see here the servo response completes in about 25 minutes. Over here there are responses that have not completed even in 50 minutes. So servo response is usually quicker than the regulator response. That's usually what is seen. As an exercise, take two identical adiabatic tanks in series. Obtain the ordinary differential equation describing the response of the exit concentration Ca to a step change in the inlet concentration Ca naught. So you got two tanks, identical tanks. There's Ca naught here, and there's Ca at the exit of the second tank. If Ca naught changes as a step, How does CA change? Obtain the ODE that describes this. And in this there are two cases. You take a proportional, in the first case you take a proportional controller that is adjusting no, there's no proportional controller. This is fine. This problem is fine. Perfect level control. Assume perfect level control. In the second problem, you got two tanks in series, and the first tank is loading the second tank. So you don't have proportional perfect level control. What you have is first tank loading the second tank. So the flow into the second tank is proportional to flow, let me call this flow 1, is equal to some constant k times, if this is h1 and this is h2, then f1 is equal to k times h1 minus h2. This is what I mean by loading, and I want you to obtain the ordinary differential equation describing the response of the flow out from the second tank in response to a change in the inlet flow F0. So do these two problems. To summarize, we have seen that the heated surge tank with PI temperature control is described by a second order ODE. We've solved the case for repeated real roots of the characteristic equation, and this occurs when KKC has these special values. We also obtained the unit step forcing solution, and that's stated here. For distinct real roots, we obtained the unit step forcing solution, and that solution is shown here. It's a combination of exponentials. PI control of a heated tank, the response is a linear combination of two decaying exponentials, and the PI controller always ensures that there is no offset from the constant set point. With this, we come to the end of this lecture. I hope you enjoyed it. See you next time. Thank you and goodbye.